Section 1.62, we're going to do a couple of slightly more difficult problems on limits of sequence. Let's say the sequence is given as such. Is 1 over square root of n squared plus 1, then plus 2, all the way up to plus n. And we are supposed to first show that Sn is bigger than this expression, but is smaller than 1, and that eventually we need to figure out what the limit of Sn is. Now you might wonder, should I write out this thing, for n equal to 1, 2, 3, just to be able to see it? You can, but let's just not bother, because it won't get you anywhere. Let's go ahead and tackle this the way it is. So first, we'll show this particular inequality, that is Sn is bigger than this thing. So to show that, we'll rewrite this thing to make it look a little better. We have 1 plus 1 over n to the power negative 2, 1/2, okay? Now, which is, of course, equal to, we'll flip this thing around, so n over n plus 1 to the power 1/2, positive 1/2, which is written another way is this. And we write it this way so that it looks like that, n plus 1. All right, so far so good. Then the next thing we're going to do, this is Sn, so Sn is bigger than or equal to, if you want. We will rearrange it, we'll replace these numbers with n. Okay, 1, 2, all the way. We'll simply replace it with n. So we have n squared plus n. Since this is a bigger number than this fraction, then it's a smaller number than Sn. And we're going to replace each one with this thing. Okay, n plus squared plus n, and so on. All the way, each one will have a replacement, except the last one doesn't need to be replaced. All right, so then we have this stuff. How many things are here? Well, it goes from 1 to n. So there's n things, n terms. And so this thing equal to n over square root of n squared plus n, which is, if you put the square root on everything, we have this. N squared plus n, which is equal to, you can cancel one of them out, and you have the result as square root of n divided by square root of n plus 1. And as you notice, this is exactly this thing, and therefore we have succeeded the first part of the proof, that Sn is bigger than that. Okay, because we have shown Sn is bigger than this thing, and this thing is exactly that, which is the first thing that we're supposed to show. So we've shown this first part, and then the second part we're going to show is that first we showed what Sn is bigger than, now we're going to show what Sn is less than. Actually, we probably don't even need the equal sign. But anyway, well, given that we are trying to show inequality, we'll get rid of the equal sign, because we're replacing it with a number a lot bigger, so it wouldn't be equal. Anyway, so the other way is we'll show that Sn is smaller than something. We will then replace this thing with just 1. Okay, we'll replace everything with 1. So Sn is smaller than 1 over square root of n plus 1. And we'll keep doing that. Everything will be replaced with 1 plus 1. So the first term is identical, but after that, everything is, this value is going to be bigger than that because the denominator is smaller. So we continue doing this all the way to the end. Everything is replaced with this, squared plus 1. And this is, of course, equal to, so there are n things here. So we have n over square root of n squared plus 1. And that equal to n squared over n squared plus 1. And what is that? This fraction will go to 1. All right. So this goes to 1, and then we have shown that, and what does this go to? Now this fraction, so we show that Sn is less than, it's going to be less than 1. That's because this is where this goes to. And then this Sn is bigger than this fraction right here. And where does that go to? That is going to go to 1 as well, as you can see here. As n goes to infinity, this thing value goes to 1, which shows that since Sn is squeezed by 1 on both ends, we have proven, therefore, that Sn is going to go to 1. And that concludes our proof. And the next problem we are going to look at is, so let's say if you have a value c, okay, c is bigger than 1, we're supposed to prove the limit as n goes to infinity of c to the power 1 over n is going to be equal to 1. And after that, we will show that even if c is less than 1 but is positive, the limit of 1 over n is going to be 1 anyway. But first, we'll show the first part, okay? Say if c is bigger than 1, then c to the power 1 over n is going to be bigger than 1, okay? Because when a function, because if a is less than 1, then a to the power n is going to be less than 1. So if this has to be bigger than 1, otherwise if this is less than 1 anytime, then the number itself has to be less than 1 as well. So this has to be bigger than 1. Because when you multiply a number by something that's less than 1, it's going to end up being less than 1. The more times you do it, the less it gets. Okay, so we have, here's the trick that we pull. We let xn equal to c to the power 1 over n minus 1. And notice that because c1 over n is bigger than 1, this thing is going to be bigger than 0. So xn is positive. So we don't have to worry about anything weird happening. So then, to rewrite this thing, we have c of 1 over n is equal to xn plus 1, or 1 plus xn, which means c is equal to 1 plus xn to the power n. And this is bigger than 1 plus n times xn. This is a very handy formula that we mentioned earlier and have used several times. It's something when it's raised to a power, it's going to be bigger than the power multiplied by that thing if you start with 1. It's a very convenient situation to memorize because it seems to be useful sometimes. So then so the c is bigger than that, and then let's from this inequality, c is bigger than this stuff, we extract xn. So xn, which is positive as we have already stated, is going to be less than c minus 1 divided by n. All right, which means as n goes to infinity, xn goes to 0. So that's looking pretty good. Which means if xn goes to 0, then it would mean, of course, that c, from this equation right here, when xn goes to 0, c1 over n will go to 1. So that means c1 over n has to go to 1. And that concludes our proof of the first part, versus we have to show limit of c1 over n goes to 1 when c is bigger than 1. Now what if when c is less than 1? If c is less than 1, then 1 over c is bigger than 1. Okay? So then the limit of 1 over c to the power n is equal to 1, and which means 1 over n, sorry. So this relationship applies, which means the limit, if it goes to 1, then the limit of just the c1 over n, it also goes to 1 as well. So it quickly uses the previous result to prove even when it's less than 1, the result is identical.